Hello everyone, we're back with another episode of Computer Vision Talks, and today we are going to discuss a paper around network calibration, which was accepted at CVPR 2022. And we have with us Bing. Bing is currently a research associate at ETS Montreal. His research interests include deep learning, computer vision, and medical image analysis, with over 10 published papers in the related fields. He got his PhD at Institute of Automation, Chinese Academy of Sciences in 2015. He also has industrial experiences at companies like Alibaba and Kuhn. Over to you, Wing. We look forward to hear more about the paper and the work.
Thank you for the introduction, and thank you for inviting me to this event. So here today, I'm going to present our recent work in CVPR 2022. The title is "The Devil is in the Margin-Based Label Smoothing for Network Calibration." It's a joint work with Ismail Ben-Ayad, Andrew Gadrin, and Jose Doze. So the topic of this paper is about calibration. So the first question is, what is calibration? So let's see this figure. With a deep learning model, a deep learning model can usually output two information. The first one is predict label. Let's see this example. We have this input image. It can predict it's a dog. And there is also a second information, like the score, probability, or also called confidence, that it will present like probability between 0 and 1 to present the confidence of the prediction. So most of previous work in this community are only focused on improve the accuracy of the prediction label. But also the other information, confidence, is also very important. So we have this calibration. Calibration is about to measure the confidence of the model in its prediction. So if a model is perfectly calibrated, we can say that its confidence is equal to its accuracy in general. But for poorly calibrated models, there are two cases. The first case is they are overconfident. That means the confidence is larger than the accuracy. If a model is underconfident, the confidence is just smaller than the accuracy. So we know to measure the prediction label, we usually use accuracy, precision, or record for that. For calibration, we also need some computational matrix to measure it. So here is the most important metric in the calibration. That is the expected calibration error, also called ECE. The matrix is very simple. With some testing samples, we can group the samples into different bins based on this confidence. Then we can compute the absolute difference in each bin, and then we do the weighted average of the different bins. Then we got the ECE score. Let's look at the figure. When we plot the accuracy with rebound to the confidence, we can have this figure. So our expected figure is the red dashed curve, but we usually have this kind of blue curve. And so the metric of this is try to measure the gap between the expected curve and the real curve. So for this metric, the perfect metric is that means that ECE is equal to 0. So our goal here is to try to get the ECE as close as to 0. So while calibration is very important, especially for some crucial practical deployment.
Hey Bing, there's a question. Can you explain what BM is here in the last slide?
Yeah, okay. BM, the big B means represent a bin. A bin is that we have some samples. We can group the sample into different bins based on its confidence. For example, in this figure, if we want to have 10 bins, we can, for each bin, its range of confidence can be 0.0 to 0.1. It's the first bin, and the second bin can be 0.1 to 0.2 of the confidence. So BM represents the bin, the M's bin, and then we can calculate the accuracy of each beam based on the normal accuracy, and then we can also calculate the confidence based on the average confidence of the testing samples in this beam. Is that clear?
Yes, to me it was, but yeah. So Himanshu, in case you dropped out in the middle, I'll just post the talk on YouTube as well, so maybe you can check it and feel free to ask more questions. Yeah, thank you.
Okay. Yeah. Okay. So here, for example, one way, I think most of us will check the weather report every day. So besides we check if it's a raining day or sunny day, we also need to check the score, the percentage of raining, like which is also important for us to plan our activity today, because the 60% of raining is so much different than the 85% of raining. So in this case, we want this probability to be accurate, to be reliable. For some other safety sensitive application like autonomous driving or medical diagnosis, when we need the score to be accurate, can also need the score can really reflect the power of the model. If the model is not confident about the prediction, it's fine to give us a not high score, but we don't want the model to be overconfident, which is sometimes risky in this application. So here the problem is that deep learnings tend to be poorly calibrated. There are some recent papers have demonstrated that deep learnings tend to be overconfident. So this the first figure is from the very original paper in SML 2017. It's the first paper in deep learning to reveal that deep learning is poorly calibrated. We can see this figure. We can see these figures. Oh, sorry. The predicted confidence tend to be larger than its real accuracy. And the main problems behind the calibration is that the first of all, it's usually use cost entropy as the learning objective. In cost entropy, it has a hard label. It means that the goal is to push the prediction to match the hard ground truth, which is to let the scores on the right class to be as equal as to 0, while the scores on the other nodes tend to be 0. And because the deep learning tend to be very highly competitive, so it's very easy to be overconfident. So let's look at the second figure. In second figure, it presents the overfitting in deep learning. We can say that even though the accuracy in test classes is not overfitting, it still decreases. We can see this orange curve. It means the test classification error. The test classification error decreases, but at the same time, the ECE on the test set start to increase. It means that the model is overfitting in probability error rather than its classification error. It means that the classification error can still be decreased, but the ECE is already in overfitting phase. So to solve this, to address this issue, there are a lot of papers in this topic already. So there are two main categories of the method. The first one is the post-processing method. In this method, we are doing a post-processing method with already trained models. The most simple one and the most famous one is the temperature scaling. In this method, it tries to add a temperature parameter on the softmax layer, and the parameter is calculated after the model is trained. And the other category of method is training method. It's can considered as a one-pass method. We train the models by considering its calibration as well. So we can, after the model is trained, we can already have a well-calibrated model. It's very interesting that okay.
Yeah, I'm sorry. sorry to interrupt.
Mm,
The one question that came to my mind with the post-processing method was, isn't it a
yeah,
bit similar to fine-tuning?
it's not. It's different than fine tuning. In post temperature scale, it's you can consider it add another layer on top of the model. So in this post processing method, we fix all the parameters of the method. We just kill the additional layer.
Oh, okay, okay. I see.
Yeah.
Thank you.
It's like we add the additional layer and we kill the additional layers based on the calibration matrix. It's
Okay,
a little different from the training process.
so it's not like fine-tuning because you already have you have a neural network on which an
Yeah.
additional layer is being added.
Yeah.
Okay, okay. Awesome. Thanks.
Yeah, it's very interesting that I think we are already very familiar with some improved loss like label smoothing and focal loss, and some recent paper find label smoothing and focal loss can also be very helpful for the calibrations. Like the focal loss can almost achieve the state-of-the-art performance in calibration as well. It's very interesting. So in this paper, first we try to understand why this calibration losses working, why they work. Based on that, we propose a constraint optimization perspective that can unify all the previous losses and can also explain why they are working. And also based on that, we found there are some problems, some issues in these losses, and then we propose a very simple and very flexible solutions to improve that. And at last, we did a lot of experiments on a variety of applications and to prove and to demonstrate our perspective and to provide better results. So first, let's look at some notations we will use in these presentations. With the deep learning networks, it usually output a logic layers, which is the layer before the softmax. And here are some typical values of the logic layers. It can be usually in the scale of 50, usually range from -10, -20 to positive 50, like something like this. And then after the softmax layer, we can get a probability like score. It will range between 0 to 1. And so in this paper, we define another matrix, which is the logic distance. The logic distance is that we calculate the logic distance by calculating the difference between the maximum value in the logic vector with respect to the current node. For example, if we have this kind of value in the logic distance becomes this one. So it's like a matrix to calculate the difference between the maximum logic with the current logic. It can intuitively we can consider it as a metric to measure the difference scores between different classes. And also we usually use cost entropy to train the whole neural networks in end-to-end manner. So here is our first perspective. So on the left, there are some formulations of.
Sorry to interrupt again. Before we move,
Okay.
there's a question in the chat. What's the intuition behind choosing maximum logic as a reference for distance?
Yeah. So, okay. The intuition is that because the confidence is calculates the definition of the confidence is the maximum value of the softmax score. So the maximum logic is related to the confidence. That is it's the value between the softmax layer of the confidence. So that's the intuitively we choose the maximum logic because it's closely related to the confidence of the model.
Okay, I hope it answers you, Himanshu. If it does not, okay, awesome. He says got it. Okay, and when you were talking about the temperature scaling method, they actually work on the softmax layer, right?
yeah, tangential scaling is like they add like a t in here, lk divided t in the softmax. It can make the softmax a little smoother because the softmax, the curve of softmax is very aggressive. So with temperature scaling, it can actually make it smoother to decrease the value of the softmax.
Awesome. Okay, thank you. Please go ahead.
Okay, so first of all, we in this paper, first of all, we want to check why the losses like label smoothing, Foucault loss, why they are working. So we try to rewrite the function and rewrite the formulation of the losses. It's not very hard to get this kind of rewritten formulation, but surprisingly, we find that they have very similar formulations. So both of these three previous state-of-the-art losses can be decomposed into two terms. The first term is just as equal as to cross entropy. So the real magic is that they add a second term, which is a penalty term, alongside with the cross entropy. And we can see that in the label smoothing, it's the second term is the KL divergence between the uniform distribution and the predictions. And for the Foucault loss and the second one is the second method is to add a negative entropy of predictions into alongside with the cross entropy. So they are closely linked. They are very related. So, and in this paper, we further prove that this second term they are actually soft penalties for this kind of equal constraint optimization problem. So here the main object is the cross entropy, and the constraint is to try to push the logic distance be equal to 0. So yes, so it's because we can say intuitively label smoothing is try to make the prediction to be close to uniform distribution. So we know that the uniform distribution, if we have two classes, a uniform distribution is that the prediction on each class is 0.5. So intuitively, it makes sense that in this case the logic distance is 0. It means that the logic value between each classes are equal to each other. So that's the magic of all the losses, because actually the cross entropy is try to push the logic distance to be as large as possible. It's because it has a hard labeled cross entropy. So that's our very interesting finding. And here if you are not familiar with the soft penalty method, we can check this definition. Soft penalty method is a very simple and very efficient method to solve this kind of constraint optimization problem. It tries to replace the constraint with a soft penalty, and the soft penalty just need to satisfy the two conditions. The first one should be continuous and differentiable in every point, and second one, it should reach the minimum when the constraint is satisfied. So with this penalty, we can solve this constraint problem by very efficient and very simple constraint optimization method like gradient search. And during the training loss, when the penalty of the second term decreases, the constraint tend to be satisfied. So actually, these two losses, they are just different forms of different soft penalty functions regarded to the same constraint. That is, the logic distance is equal to 0, and they only differ in its gradient dynamics, because the objectives are all the same. So here's some brief proof of a brief introduction of the proof. It's not very hard. We just prove it by the expression of the softmax and the KL divergence. And also we use a property of the log sum exponential. You can refer to our papers for details. I don't want to, we don't need to detail this proof here. So here it's very good to unify all the losses in the same formulation, in the same framework. But we also find the problem here. The problem is that the constraint of logic distance equal to 0 is a trivial solution, because it prefers all the logic to be equal. So in this sense, it's the model lost all the discriminative probability. And as we know, it's just because they are just using the soft penalty terms. So this objective can only consider as a trade-off term alongside with cost entropy, even though it will not be achieved in real applications. We argue that this objective is not very ideal. So based on that, we provide our solution is that we kind of generalize the constraint. We generalize the equality constraint by the inequality one with a positive value that we noted at the margin, by a positive margin. So in our solution, we only need to penalty the logics where the distance is above the margin, because we don't think we think it's trivial to push it into to be equal for each logic. So in our solution, we can it's guaranteed that the process can always optimize toward the informative goal. We can check on the right is a very intuitive figure about our ideas. So in the left it's kind of the optimizing direction of the label smoothing of Foucault loss. We can say that it continually push the logic distance to be 0 alongside with the optimization process. But in our method, we just penalty those logics that is larger than a particular margin, because we think it's not necessary to push it forward to across the margin. So, and also in this, by our method, we think it can help to achieve the better balance between the accuracy and the calibration. So here is the formulation of our method. It's very simple. We just add inequality constraint alongside with the cost entropy, and also because it's not very straightforward to solve this constraint optimization in the sense of deep learning. So we further use the soft penalty method by the remove functions. We transfer this constraint into the remove penalty, and we also introduce a balancing weight between the two terms. But in our experiments, we keep the balancing weight to 0.1 in all the experiments. So here we just need to tune the margin M, and by this way we guarantee that we have the same hyperparameters budget with related to all the previous losses, like label smoothing or Foucault loss. So here are the experimental part. So first we did some experiments on the standard image classification benchmarks, that is the TNA ImageNet and the CIFAR 10. The first table represents the calibration result. And here we use the ECE metric, and also with the adaptive ECE, it's like a variant of ECE. So on both metrics, our method can achieve the best calibration performance compared to all the related losses. And the second table is that we demonstrate that our method actually have no cost for discriminated performance. Basically, all the previous losses they kind of sacrifice some sort of accuracy to achieve better calibrations. But our method, we have nearly no cost of the accuracy. And here is the result of the fine-grained image classification. We designed this experiment on fine-grained image classification because we think in this kind of task that it can be harder to achieve better calibration because all the classes are very close to each other. So it's very good that our method can achieve the best result both on accuracy and the ECE. And in our framework, we argue that label smoothing is just a special case of our formulation when the margin is equal to 0. So here we design an experiment to demonstrate that. So here we set the margin to 0 in our method, and we compared it with label smoothing by varying the balancing weight of the two terms. It finds that all the results are very consistent with each other, and the trend and the value are also very close. So this validates our perspective that label smoothing is just a special case of our method when the margin is equal to 0. Here is some ablation study on the margin and the balancing weight, and our method can provide stable solutions. Here is another two kinds of experiments. The first experiment is conducted on the semantic segmentation of VOC 2012. And on this task, we also achieve better calibrations, and also we slightly improve the IOU of the method. I think our method can also help to improve the IOU because we can somehow prevent the overfitting of the model. And also we did another task on NLP classifications with 20 new groups. And we also obviously improve the ECE by a large value. So here because our method is actually a very general framework, and it can be easily plugged into any kind of pipelines. So we prove that our method can be very good on different kinds of classes and different kinds of applications. So here are some visualization results of the calibration loss. So as I mentioned, our goal is to let the blue line to be as close as to the red dashed line. So here we can see our method and did the best. So for the cross entropy, it tends to be in the overconfident phase. In the label smoothing and the focal loss, because we already say they are too aggressive by pushing the logic distance to 0. So usually we achieve underconfident models by these two kinds of losses. But in our method, we did a better balance between them. So our method is much more closer to the perfect calibrated model. Yeah, here are some very interesting results on the segmentation task. In this visualization, we plot the confidence map of the models, and we can see that in our method, it's much more close to the real condition. That the model is very confident in its within region and in the outside region, but it's kind of not very confident in the boundaries. But in the loss such as the focal loss, it's become also very underconfident in this within region, which is not very good for the model. So okay, here is the link to our website and our code, and I think it's very easy to try it, to play it, and also it's very easy to plug in the loss into your pipelines.
Yeah,
okay, here's a very brief presentation when we have some time to communicate with each other.
Awesome. Is this the same presentation that you used in CVPR too? or did you
Sorry,
extend it? Is this the same presentation you used in CVPR or did you extend it?
I extended it because in CVPR it only gave us 5 minutes for the
Okay.
presentations.
Yeah. I was reading tweets about people doing their presentation in 2x mode so that they can finish the 10-minute presentation in 5.
Yeah.
Interesting. So I do have a question. So recently hi Dean. I can give you option to unmute yourself and then you can have a conversation if you want. Okay, awesome. So there's one thing I would really like to know. If you have to explain network calibration to a kid who's new to ML, what would you use? It's not fine tuning. It is not modifying parameters. How would you explain network calibration to a kid?
Yeah, I mean, calibration is like it's like another it should be another property of the model itself, because we usually we only focus on the accuracy, which is a measure of the predict label. But the calibration is another metric of the model about its probability or its confidence in its predictions. So yeah, it means that we should consider it's not a new parameter, new layer. It's just we need to consider the calibrations when we train a network or before we use a network. So it's a totally different. It's a different topic.
And when we are talking about confidence of predictions, more recently, all the work that have been centered around knowledge distribution paradigm try to reduce the confidence of a model, right? So, sorry. So my question is that reducing the confidence of model versus calibrating the model that is like the teacher model. Do you think it's going to make a difference? How is it different?
Do you mean decrease? I think it's maybe different papers do different things. I think maybe some papers they try to increase the confidence. Some papers they try to decrease the confidence.
Yeah, sharpening, smoothing.
Yeah, I think it's very related to the calibration because we are all try to focus on the confidence of the models. The calibration means that the confidence is just equal to its real ability, to its real accuracy. So if we want sometimes like you mentioned in the knowledge distillation, we want to model to be overconfident or confident in different cases. But here we are trying to make the model, the confidence to be just right, to be just equal to its accuracy.
Right. And is this your first work around network calibration?
Yeah.
Okay. How long did the paper take?
The paper, actually it took a long time. Actually, last year it's a work with the main ideas are from Jose and I, and so actually we had this idea in around April last year, and previously we prepared to try to write a paper for new RIPS, which is in around the middle of May, but we didn't have very good results. Then we tried to achieve the clear, which is in the it's in around September. But we also didn't get a very good version of the paper. I think we are at that version. It was enough to submit, but we thought it's better to keep it now. We want to. It's not very good to submit a half-cooked paper because we need first to convince ourselves, and then we are able to convince the reviewers. But I think that's very good. That was a very good call to skip the ICLEARs, because in between the time of ICLEAR and the CVPR, we have a great improvement, and we make the method much simpler, much easier to use. And we also did a lot of experiments on that. So I think so before CVPR, we prepared very well and we have very good papers. So I think that was good. We don't need to rush into something. We just want to make our paper well presented and well convinced. Then we submit the paper. Yeah, actually it took a long time. Took more than half a year.
Okay, don't say more than half a year. It's been half a year me trying to work on a problem with no solution. So yeah, a long time sounds.
Yeah, because it's maybe a short for a new area, but I mean we already have the ideas. We have ideas in April, and we finally make it in October. So yeah, it's a pretty long time because we already have the idea and already have some good original results.
Right. Okay, two more questions from my end. One would be, when you're talking about having an idea in April, how did it strike? Where did it origin from? Like, what was the initial motivation that brought you into network calibration? Because this is your first work, right? So did you find a drawback? Did you find a loophole? How come you got into network calibration? And what were you doing earlier?
So do me how we find the topic of calibration and how we find the idea. Yeah, I think it's the topic was mainly from Jose and Ismail, because I think Jose had already did a very good presentation here. He presented his idea of the cross entropy. Yeah, I think this work is just very close to the application of the entropy and cross entropies, because they are very related to the confidence of the models. And also in the work of our team, we don't want to achieve the complicated architectures or any kind of like this. We want to truly understand the magic behind the performance. So that's why in this paper we first try to understand understand the problem of calibration and understand why previous losses work, and based on that we're trying to improve based on top of the other losses and on top of the optimizations. So actually in the first step we also did a lot of things to plot the distributions of the softmax. I mean let's see. Yeah, I mean we did some realization to check the distribution of the logic and to try to see what's the distribution logic in different data set, different classes and different networks. And then we find that we can define this logic distance, which is very good to help to improve the calibration to regulate the network training.
Yes, and even the code, like I've seen it, I've used it, and it's very clean and easy. Like you can just take any network and you have a logic-based loss function to introduce, and it's super easy to use in any network as such. Yeah, it's not super complex. Or yep, that's nice. That's nice. Yeah, and one question, Bing, which is not related to paper but related to you. You were in industry and then you moved to academia. Now I'm curious what motivated it. And are you going back to industry anytime soon?
That's I think that's a tough question, and I think sometimes we are doing network prediction, but we cannot predict our future very well. But I think my goal is I want to try to do some work that is impactful, that can impactful for the community, for the application, for the customer. So when I got my PhD, I was very curious about the work in industry, and because they have very good data, they have computation ability, and the application are already used by a lot of users. So that's my motivation to go there to use the data to try to implement better applications, and then the reason I came here is I think it's mainly because of Ismail and Jose. It's because we talked with each other for some time, and I think they have very good foundation and a very good plan, and for the research, and I was fascinated by that, and because I was curious to work in Canada, in an international environment, because before that I was living in China from birth till then. So it's also a very good opportunities. And also I feel in a big difference in academia is that in academia we have better freedom to really dive deep into a specific field and to do impactful research work, because in industries we don't have so much freedom, and we don't have the time to really go very deep into the task. Usually we get a good result on a specific task, then we are required to move to another applications.
Yeah,
so
right.
that's very different. But for my future, it's not very predictable. I'm still trying to think of the questions you are asking. So I think every time I kind of have different answers to that.
No pressure, no pressure. I can totally relate and understand the first part. Even like when I'm talking with, I love the culture of, reassessing the complexity that's going on in ML right now and coming up with easier alternatives which perform way better. That's Jose's approach, and that's why I totally love the idea of reassessing everything that's going on and proposing easier things. But there are 2 questions in the chat regarding the paper. The hyperparam M is in logit space rather than probability space.
Yeah.
Okay.
Yeah.
If yes, would the distribution of logits affect the selection of M? I'm thinking from perspective that the behavior of logits can change from tasks to tasks, making it difficult to select M.
Yeah, I think that's a very, very good questions. So yeah, we had some discussion. We can also, of course, we can also impose the hyperparameter, impose the constraint on the score after the softmax. But in our experiments, we find imposing the constraint on the logic layer can yield better results. I think because that on the logic layers, it can be more close to the network, and it can be better for regulate the training process. And also I think it's the task, the hyperparameter M is related to the data set. I think it's in our experiment we find it's actually related to the classes, to the number of classes. For example, in the CVPR 10, we can see this. In CVPR 10, we find the best hyperparameter, best margin is around 6. But in the ImageNet, which has 200 classes, the best hyperparameter, the best margin lies around 10. But in this curve, we find that it's the margin, when we use different margins, the results are not so much different. It can always deliver us better results. So that's why in our experiments on ImageNet, segmentation, and on the NLP, we fix the margin to 10, and we can get stable results. I think maybe 10 is a good starting point to tune the hyperparameter.
Himanshu, you can also unmute yourself if this doesn't. Okay, he gets it. Thanks. There's another question. Did you consider cases where the margin is dependent on the class?
Yeah, that's also a very good question, because I think for different, it's very makes sense. We have a different margin in different classes, but actually, we are trying to do this. We are doing some experiments on this, but we didn't play with the margin. We play with sorry. Actually, we didn't play with the margin. We actually play with the balancing weights, because we are trying to use some optimization techniques to make the balancing weight to be the balancing weight lambda to be adapted for different classes. Yeah, we are also trying to think of, yeah, our idea is that very close to that. We want to have adaptive margin, but we find it technically difficult. So we are trying to do some experiments on adaptive lambda, and the experiment is still ongoing. It's not so good yet, but we are trying to improve it.
Nice. I see. Although our audience has been joining a lot today, network instability is not limited to Canada, maybe. Okay. I think these were the questions from us. If anyone has more questions, feel free to drop in the chat. And yeah, I'm done with my questions. I asked a lot of them. So yep. And the good thing is, because Bing is my colleague, so I usually get up from my table and hop onto his to ask questions at least twice the day he visits. So I get to disturb him, but you don't. So you can reach out to him on the social media links that he gave. He is there on LinkedIn. Yep. And feel free to check out the paper and the repository. Okay, I think that is it. Thank you so much, Bing. It was great to talk more about the paper. And this was our first time talking about network calibration, my first time exploring network calibration. And it is definitely interesting and also essential. I'm amused that we don't include it in the process of training the neural network.
Yeah, thank you for inviting me. It's very fun to be here.
Thank you. Okay, see you. Goodbye, everyone.
See you.
Have a good weekend.
Goodbye. Yeah, have a good day.
Yes.